mic. It's good. Makes me wonder, before electronics was available, how do people preach in a church?
They just yell really loud.
No, it's the way the building is set up, That's what
Acoustics.
I think.
They have really good
Because
acoustics.
it's such a huge, speaking from a diagram and all that.
Still have to yell.
And plus, they don't have people chatting and eating and drinking.
I think
And on their
that's.
cell
The parents would just smack
I
their
think
kids.
people absolutely chatted and ate and drank.
Ah.
I don't know.
Passing out the bread.
Okay, so you guys get a choice. Do you want me to explain the solution to the homework assignment? Or do you want to move on to kind of how do we make use of the interrupt call so that we can request services from the operating system?
Whatever's most helpful for the test.
I cannot say because I don't have the test yet.
I think interrupts would be.
Interrupts? Okay, so we'll go through interrupts first. If we have time, we can go back and take a look at the homework assignment. How many people finished the homework assignment? Okay, well that's good. Okay. All right. So what I will probably do is I will give you a solution to the homework assignment for those of you who did not finish the homework assignment and you want to see a solution, not necessarily the best or the shortest, but a solution. So I will just give you the solution to the homework assignment, and then we'll just focus on the last topic, which is not going to be a big deal. I mean, trust me, compared to passing structures and returning structures, this one is going to be a walk in the park. Oh, it is. It's easy. So I fixed all the links already, so all the links are now going to work. And this one, I'm not sure whether it works or not. It obviously doesn't work because it's not actually my link. But you can search for this too. System, Linux, system call table. There are multiple of these. Here's one. Okay, so this is a table where on one side you have, okay, we'll focus on the second column first, the name column, okay? And don't mind the cis underscore prefix because they all have the same prefix. So what you will be focusing on instead is the name or the word right to the right-hand side of the underscore. So you have exit, you have fork, you have read, write, open, close, wait PID, create, and so on and so forth. That's basically a base set or a core set of functions that any application program will need in order to do anything useful. Okay? But at the same time, these are also requests that an application program can place to an operating system. In other words, you can ask the operating system and say, I would like to exit. I would like to read from a file. I would like to write to a file. I would like to fork, which means I want to create a new process. Okay. I would like to wait PID, which is waiting for another process. Okay. You want to do a create, which is creating a file. Link and unlink are actually misnomer for the most part. Unlink is actually remove, okay, delete file. The rest, I can explain some of those pretty quickly. CHDIR, I think some of you might have used it in this class. It's CD. It's the same thing as CD or change directory. Time, make node. Chmod is change, well, it's changing what we call the mod flags, which is changing the permission to a file. We have stat, which is checking a file. Seek, which is moving to a particular position of a file so that you can do file seeking. And we have a whole bunch of other things. We have pause. We have kill. Kill is a misnomer again. The kill call is not actually to kill another process, even though you can use kill to kill another process. But what it really does is to send what we call a signal to another process, which does not necessarily kill the other process. But it's one way to communicate, for processes to communicate. And then the rest, we can see we have mkdir, creating a directory, render to remove a directory, Pipe is an interesting one, because it's basically, it creates two file descriptors. One serves as an output, the other one serves as an input, and they're connected. So you're basically making a pipe. We got Signal, which is a way for inter-process communication, and a whole bunch of other things. Okay, Chroot is useful because it helps you create a sandbox so that even if a program is hacked, it will still be inside the sandbox. So all of these are things that you can ask the operating system to do for you, or you can make the request. And now we start to look into, hey, we know this term. We know what is an EAX. It's one of our registers. And then we look at these things here. And when you look at not the column heading, let's just pick read here, okay? So if you look at read, this is saying the first parameter to read is an unsigned integer. It is the file descriptor. And the second parameter is a char pointer, because that points to an area in memory where the content of a file is read into. And then the third parameter is size_t, which is basically an integer, because it tells the operating system how many bytes you want to read. So we kind of do okay in terms of how to read this table. Okay, all right. But I haven't explained the first column. What about these? The 1, 2, 3, 4, they just seem like consecutive items, but they're not really just identify which row we are talking about. These are the values that you need to put into EAX when you want to request that particular service. In other words, in this case, if you want to delete a file, okay, to delete a file is unlinking, okay, you have to put 10, the value 10 into EAX, and then you have to specify the name of the file that you want to remove. You want to put the address to the name of the file that you want to remove into register EBX, and then what do? Do you guys remember from the previous class, and also actually many other classes? What is the last instruction that we need to use in order to get the attention of the operating system?
Int 80.
Int $0x80, okay? Because it's called a software interrupt instruction, which means it is a software instruction that triggers the very same mechanism as a hardware interrupt, which involves a few things, okay? It involves elevating the privilege level, okay? That's the first thing. The second item is go through a vector table that contains the jump addresses or the entry addresses. And then it will go into a subroutine, which in this case is owned by the kernel, the operating system. The operating system will try to do the operation, but when it returns, it's going to return back to your program, just like a normal return, but it will also change the privilege level back to your normal process privilege level. So when it returns, you're not going to gain any increased privilege level. So are we kind of making the association here? So what we'll do is we'll try out a few of these things. Okay, maybe not fork, because if you have an infinite loop that is creating more and more processes, you can hang up a system pretty quickly. How many people know what is fork? Okay. How did you know about fork?
Oh, GitHub.
Hmm?
GitHub.
Oh, okay. So all of these, you can also do a man page. The man page contains entries for all of these. So if you say man fork, it will tell you, fork is one of the functions for basic process management. So a fork is interesting. I'll just do a very, very quick introduction to fork. It's interesting because this is how a process replicates itself. Okay. In other words, let me go back to my paper here. Okay, so I'll just give you a fragment of a code. Okay, so this is typically the instruction or the statement in C to make use of fork, so that out of one process you end up with two processes. Okay, so but they're clones of each other. In other words, these two processes are running exactly the same program at exactly the same point. So the question now is, how do you know whether you are the original process that is asking the operating system to clone yourself, or are you the actual clone? You just started to exist. Well, the answer is you cannot tell from the variables, or the global variables, local variables, everything, because they are identical between these two processes. The only thing that's different is the return value of fork. So if you go back to this point here, fork is creating two new processes. The return value is 0 in the child and the process ID of the child in the parent. Okay? So what that means is when you write a program like this, the very next statement should be a conditional statement to basically ask, is PID 0? Okay? So if PID is non-zero, then you know that are you the parent or are you the child? Are you the process just created, or are you the one requesting a new process based on documentation? You are the requester. You are the one who requested a new process. So in this case, you are called the parent process. Okay, let me see if I can make the focus a little bit better. Not a whole lot better, but it's okay. The other one, if you go to the else statement, then you are the child process. And based on whether you are the parent process or the child process, now we can do processing, different processing, and do things that are actually useful. So this is how the Linux operating system can start with one single process when it boots up, and then we can have like hundreds, if not thousands, of processes by the time it's up and running. And I can show you this little map here that can be kind of useful. Okay, these are optional stuff. You don't really have to. I cannot ask you questions about these, but they are kind of useful to know, I think. So ps-al-forest. Okay. So this is how we look at all the process and the process IDs. You know that this is process ID, this is number 2, and this is PPID, which is the parent process ID. So these are all processes that are created from PID number 2. I don't know what happened to PID number 1, because that should be a PID number 1, but it doesn't seem to be listed here. That's the very first process of the entire operating system. Okay. But it does show you the parent-child relationship using the tree type of relationship. So when we get to this part here, we can see login is leading to bash, which is the command shell. And we are running out of space to show all of the other ones, but this particular bash running less is a part of the bash, which is a part of the terminal program, which is a part of the desktop process, and so on. But if you track it, you can actually see the parent-child relationship of all these processes. Okay? So just a little bit of fun stuff, about fork. So what we'll do is, let's say we just want to create a program to delete a particular file using unlink. Okay? So we want to figure out how to do it in assembly. Let's go ahead and just create that particular test program. We'll lock everything into a folder just in case I run the delete incorrectly and maybe deleting something that I don't want to do. So we'll just create a test folder, go to the test folder, and touch a file called garbage. Okay, this is something that I want to delete. And I will go ahead and write a program to delete this one file called garbage. Okay, so we have the usual stuff under .global_start. This is not a subroutine of anything, so this is a self-contained assembly language code. So we have _start. Okay, so the first thing is to move something into EAX to specify the operation. Looking at this table, can anyone tell me what is the value that I have to put into EAX?
Unlink?
Unlink has a value, has a number of
10.
10, that's right, okay. So 10 is the number to identify, hey, I want to ask the operating system to delete a file. So put that into EAX. And now I need to put a file name into EBX. So the quickest way to do it is simply to create a label called file name, ask keys, A-S-C-I-Z, because I have to make sure this is null terminated. And then we spell out the name of the file that we want to delete, which is garbage. Garbage. There we go. So move L, $file name into EBX. So we're almost done, but don't forget this one, because if you forget the int instruction, then nothing is going to be done, because the int instruction is the entry point to the operating system. Every single time you want the operating system to do something for you, that's the entry point. EAX identifies what kind of service you're requesting. EBX, ECX, EDX, and so on, they are parameters, okay? Because in certain operations, you might need some additional values. So those other registers is just to supply the additional parameters. Like in this case, EBX is pointing to the file name of the file that I want to delete. Okay. So after this, I can exit the program, which is putting a 1 into EAX, because according to this label, if you put a 1 into EAX, it is the same thing as a system exit. Now, if you want to look up additional help about, okay, but what does it mean when I exit from a process, you can just go to any command prompt, or even inside the editor, you can shell out and say man exit, and this explains what exit is all about. Okay, exit does have a status, which is the parameter that we are passing through EAX. So back to this program. We put a 1 into EAX to specify we are exiting, and the normal exit code is 0, so we put that into EBX in this case, and then we make that request to the operating system and say, okay, I'm ready to exit. So that's why in this program we have two int $0x80, because both of those are entry points to ask the operating system to do something, but what you're asking is specified by the value of EAX. EBX serves a different purpose each time. The first time is a pointer to the file name. The second time is simply the exit code. Do we have any questions about this program? Any questions about the first 3 lines of code is to delete a file, and then the next 3 lines of code is to exit the program? No questions? Okay, let's go ahead and just run it. Now, when we run this program, we also want to observe, okay, but what if the operating system cannot do it? How does it come back and tell me that, hey, this operation failed, okay? So in order to understand that part, let's look at unlink here, which is a call, and it has its own man page. Well, that's not what I want. Okay, maybe man 2, okay, because there are different, what we call parts of the man pages. So this part does explain what is unlink. So unlink, if you look at the explanation, deletes a name from the file system. If that name is the last link to the file and no processes have the file open, it is going to delete the file. This is a long way to explain that Linux supports hard links, and you can have multiple names for multiple folders pointing to the same physical file. It doesn't happen very often, so for the most part, when you unlink a name from a file, it is the same thing as deleting that file.
So it's kind of like shortcuts?
They are super shortcuts. They're called hard links, which means there's no differentiation amongst the hard links. Each one considers itself as, yes, I am this file. So in order for a file to be completely removed, you have to have all the hard links removed. Whereas in Windows, if you have a shortcut, you can have the actual file removed and the shortcut still standing around being a dangling pointer. But in the case of a hard link, that cannot happen. Yep.
Well, I was going to ask about that, like
A symlink?
Basically, I was just going to ask about if after deleting it, just if the program just stays around wherever it is. Like pretty much if you just unlink a file name from something or other, but it still links.
Okay. We'll get back to that one, but the first thing I want to do is to look at the return value of unlink. So return value, on success, 0 is returned, on error, -1 is returned. Okay, so that means, But how do we do this? How do we know whether the unlink was successful or not? This is not a subroutine call, remember. But guess what? If it is an integer, it is still being passed by EAX. Okay, so even though we are now asking the operating system to do something, it is still going through EAX to return a value. Okay. All right, so getting back to this program, I think we're ready to run it. So double check, make sure my file to be deleted is here. And then we'll go through the usual process where we do the assembling, gstat-o, delete.o, delete uppercase s, ld, and gdb. Okay. All right, so we'll put a breakpoint on line 6. Okay. And just run the program. So on line 6, this is right before we actually make the request to the operating system. We can just double check stuff, okay? We can say, oh, let's see what is at the address pointed to by EBX. We'll just double check to make sure that is really the string. So we'll say display this whole thing, display 20 characters as 20 bytes as characters at the location that EBX is pointing to. Okay, we do get garbage, G-A-R-B-A-G-E. Okay, that's good. It's non-terminated. All right, so now we can do the single step. Single step, now we're at line 8. So what should I be able to observe at this point? 2 things. First of all, the first thing I want to observe is what is EAX? Was the operation successful? Right? If the operation was successful and I was able to unlink garbage from the file, then it should return 0. So I'm going to do IREAX, and it is in fact 0, which means the operating system said, yes, you asked me to unlink garbage from this file, it is now unlinked. Which also means the file should be gone by now, right? Let's double check. Within GDB, you can use an exclamation point to shell out, which means whatever you type after the exclamation point is going to be run as if it is on the usual shell. So now we can just do an ls, and garbage is gone. Okay, which is good. Okay, and we just continue the program, which will exit, and it says exited normally because the exit code is a 0 of this program. So do we have any questions about how we just interacted with the operating system, not once, but twice? The first time is to delete a file, the second time is to exit from the program. Is that all good? Okay. So next, we want to do something maybe a little bit more challenging because deleting a known file name, hey, that's, nope, go ahead.
Part of the exit code is said inferior 1. What does that mean?
Inferior 1 refers to the thread 1, but since this is not a multi-threading program, there's only one thread.
So it's just saying thread 1 exited?
Yeah. Good question. Anything else? Okay. No other questions? So what we'll do next is to look at the C program, make sure the C program works, and then we'll try to convert it into assembly code. Is that okay? All right. Let's see how much work is involved to read in a decimal number and be able to convert it into binary representation and store it. Okay. And we'll first do it in C first. So don't worry about assembly language programming, just do it in C first. So I will just say read base 10, okay, so read 10.c. And I'll just do this in one single subroutine that I'll call read 10 by itself. Doesn't need any parameters because it's going to read from standard input file. All right. So has anyone written code to read from a file that is a base 10 number? Let's say this is an unsigned base 10 number, and convert it into base 2, which is the internal representation. Has anyone done that before?
Yeah.
Okay. So how would you do this?
You can do it recursively.
Let's do it recursively.
Okay. Like the modulus operator.
Yep, the mod operator, well, actually it's not a mod. Mod is useful when you're printing, but when you are reading, it is the opposite, which is
Division.
multiply.
Okay.
Multiplication, okay, that's what you need. Okay, so we'll go ahead and start with this one. And we'll start with something safe. We're gonna say, let's see if we can actually read something. So we have a local variable, a single character as my buffer. And I say, let's try to read it, okay? And we say if read. Remember how to use the read? The first one is the file descriptor, which is going to be an integer identifying which file I'm reading from. In this case, it's hard-coded. Standard in is always 0, standard out is always 1, standard is always 2, and then there's also standard mux, aux is always 3, okay? So those 4 files are always open by the time you have a process written in C or C++. So in this case, 0 means standard in. I'm trying to read it into buff, so the address of buff goes here. And there's only one character, okay? I only want to read one and only one character. So now it returns a value. Okay, what does read return? Let's check it. Okay, so we say man to read to find out, okay, what does it do? And particularly the return value. On success, the number of bytes read is returned. 0 indicates the end of file. And the file position is advanced by this number. If it is not an error, it is not an error if this number is less than the number of bytes requested. Since I only requested 1, that means if I get a 0, it is the end of file. Okay, so on error, -1 is returned and error num is set appropriately. Let's say that it's not going to get into the error condition, just to simplify this code a little bit. So in this case, if I just leave the condition the way it is, it basically is saying, okay, I did read something into buff. Now let's go ahead and process it. Okay. The first thing I want to do is to say, okay, do I want to do error checking? Am I only going to get digits from 0 to 9? Let's just make that assumption. Okay, so I'm not going to do error checking here. So I'm assuming the buffer or whatever character I read is going to be the ASCII code of 0 to the ASCII code of 9. That's a given already. So now we want to do some processing. It's like, okay, but what else are we going to do? Well, remember this is recursive, okay? So now you have to think about, when do we stop? When you're reading a number. What are some of the conditions that will basically say, this is the end of a number, stop?
\n.
\n, okay. What else?
No.
Anything other than a digit or the end of file should stop, right? Okay. So that means if I did not read anything for the else here, I should return a value of 0. Because there's nothing else to read, okay? I better return a 0, there's no value. Okay, so I'm going to use int result here because I don't want to sprinkle return everywhere. So I'm going to put a result of 0 over here. And then use a return 0 result here. Okay, that's one of the terminating case. The other terminating case is I did read a character, but it's not from 0 to 9, so I should also end here. So I can say if buff is less than or equal to 9, the ASCII code of 9, and buff is greater than or equal to the ASCII code of 0, it means it's valid. Okay, we'll do some processing here. Otherwise, we are done because we did not read the digit. So once again, we indicate the result is 0. There's no recursion in this case. All right. So now we want to specify, what if I read the digit? What should I do? Well, I should not return right away because there's no guarantee this is the last digit. So what I really should do is to say, well, maybe there are some other digits, which means recursion, right? Recursive call. Well, we know it's going to involve a recursive call, okay? But the question is, what am I going to do with that recursive call? And how do I combine that with the digit that I have just read? That becomes the next question. What do you think? Okay, let's just think about, from the perspective of the program, what is it going to see? Okay. So let's just say that the input has 1, 6, 5, and then the carriage return or line feed. Okay, it doesn't really matter as long as it is not a digit. It should still do the same thing. So the first digit it's going to see is the 1, or the ASCII code of 1. At that time, it's going to do the recursion. The recursion will see the ASCII code of 6, and it will see the ASCII code of 5, and then it will see the ASCII code of something that is not a digit. Then it will stop the recursion. So the question now is, how do I combine the 5 with the 6, and then that thing back to the value, back to 1? Well, what is 165? It's 1 times 100 plus 6 times 10 plus 5, right? But another way to write this is what? Is 1 times, right, I'm trying to write it in a nested way so that the recursive relationship is clear. Okay, so the 5 is on the outside. Okay, and then we have a times 10. What is inside the times 10? We've got a 6 here plus something times 10, and that turns out to be the 1. So are you guys starting to see a recursive relationship? Kind of like, oh, we're doing the same thing again, except it's one level deeper. Is that okay? All right. So based on our observation of this example, we kind of know what to do with this, okay? Except there's one problem. I cannot differentiate the case where I actually read a digit of 0 versus reading not a digit, because I need to make that differentiation. If I see something that is not a digit, I cannot multiply by 10 because I am the last digit already. Okay. So that means in this case, I have to actually store this number first before I process it. So I will say temp equals 2, read 10 recursively. And if temp is greater than or equal to 0, then I'll do something here. Otherwise, we'll do something else. Okay. Which also means in this case, I cannot use 0 to indicate that I did not read a digit. I have to use something other than 0. Okay, -1 will work. And that works with this case too. This is the easier one. If temp is not greater than or equal to 0, it is less than 0, which means I did not read a digit. Or the recursive call did not read a digit. I read a digit, but the recursive call did not. So what value should I return as the integer value that I read?
Buff minus 0.
Yep. So result is going to be buff, which is a character, minus the ASCII code of 0. Is that okay? Because if I did, okay, let's say I read the ASCII code of 5, okay? And then the next character is something other than a digit. So that means the recursive call over here is going to return a negative value. And that's how I ended up here. But I, being the current invocation, did read a digit. That's how I can get past this condition over here. So in order to figure out the value of the digit that I just read, I just have to subtract the ASCII code of 0 from the ASCII code of the digit that I just read. Is that making any sense? Because the difference between the ASCII code of 5 and the ASCII code of 0 is 5, exactly. Okay. So that part works. But what if it is non-zero? What if it's, excuse me, what if it is non-negative? And result is going to be, well, we know this part has to be here. Okay, look, I want you guys to kind of focus on the sheet of paper, which is an example of what we need to do. This is the digit that I read, okay? And this is the value of all the other digits to my right-hand side. So what do I do to combine these two? So once again, buff minus the ASCII code of 0 is the one digit that this invocation has just read. TMP temp is representing the value of all the other digits to my right-hand side. So how do I combine these two? Well, we know there's an addition somewhere, right? But in addition to the addition, there has to be something else that I have to do.
Times 10?
I have to multiply something by 10, right? How does that work? How does that look? Does it look about right? Because temp is the value of all the other digits to my right-hand side, and buff is the current digit. So the value of including what I have just read along with everything else to my right-hand side is going to be the sum of me times 10. Oops, that wouldn't work. That would not work. That doesn't work. That doesn't work, because I have to pass along the power of 10 along to get that to work. Oh, shucks. I'm still trying to think to see if there's a recursive way to do it.
Just give it a parameter, the function.
Yeah, but I don't want parameters. See, without a parameter, I cannot know how many digits are to my right-hand side, so it would be impossible to do it. The other way around, I can do it recursively, given the number, print it out in any digit. Okay, I guess I'm gonna give up. I cannot do this recursively without a parameter. With a parameter, yes, but not without a parameter. Oh, that sucks. So I just have to think about, do I want to make this work, or do I want to change the nature of the problem?
When I said recursively, I thought you were asking a different question. I thought you were asking about something else. When I said, like, oh yeah, let's just do it recursively. I didn't know what you were asking.
Let's just turn it into non-recursive form. It's just okay. Yeah, yep, that will work. Okay, non-recursively, we can do it like this. While read 0, ampersand above 1. Okay, as long as I'm reading something, that's what it's saying. And that something is a digit. So we put that into here. Buff is less than or equal to 9, and buff is greater than or equal to 0. So as long as I'm reading something that is from 0 to 9, do the following. Result has to start with 0. And so we say result equals to result times 10 plus buff minus the ASCII code of 0. That's all I need to do. But there's no way to turn this into a recursive form without a parameter. I have to use a parameter to do it recursively. All right. So is that making any sense? I'm hoping this makes more sense, because result is based on what I have read up to this point. So every time I see a new digit that is from 0 to 9, I have to multiply what I have up to this point by 10, and then add the value of the new digit that I have just read. Okay, so that makes perfect sense. This is the code in C, and we'll go ahead and have a main here, just so that we can test it before we turn it into assembly. So in the C code, I just have a local variable, say x equals to read 10, and return 0. That's my entire program. GCC-G-O
Dash capital S. Dash capital S.
To disassemble. I can probably tell whether it whether a program is the result of that. Okay, it complains and says read is not. It doesn't know about it. That's because I did not include the header file, which is UNISTD, which stands for Unix standard. So let's go ahead and include that. We're dealing with read10.c. I'll include unistd.h. Recompile, gdb read10. This is the program, put a breakpoint on line 21, run it at full speed, give it an integer. Let's pick an integer that's easy to check, 567. And then we want to print local variable x. It is 567, so the program works. Okay. All right. So now we want to convert this into assembly code. So let's go ahead and display the C code on one side and then the assembly code on the other side. Read10.c on one side, and then read10, or just r10.uppercase s on the other side. All right. So this is the assembly code. We have to do a .global read10 to export the label, read10, and then return. The usual stuff, push EBP, pop, EBP, move ESP to EBP to set up the frame pointer, move EBP to ESP to restore the stack. And then if we have local variables, which we do, we will have to allocate for the local variables. So here's old EBP equal to 0. Return address is old EBP plus 4. I really don't have to work on this side because everything is on the other side. Buff is old EBP. Now technically you only need a -1 or -1, but I'm going to do a -4 here. And the result is buff -4. So now I can adjust the stack accordingly. Add result to ESP to allocate for our local variables. Now we can move on to the actual code inside the C subroutine. Result equals to 0 is just move 0 into result EBP. Then we have a loop. Okay, so in this case, in this loop, I can do the same thing, which is push 1, push the address of buff, push 0, and then do a call to read. That would actually work because the linker will find out that, oh, you want to call a subroutine called read, and the read subroutine is within the C standard library, so it will actually link. But I don't want to do it that way. I want to request the service directly from the operating system without calling anything. So what we need to do is now to move stuff into the register and then rely on int $0x80 to get the job done. So read, once again, is service number 3. So we put it into EAX, and we need a label here because it's the beginning of the while. We need to move 0 into EVX because that's the first parameter. The address above, we have to move it into ECX, okay? And to do that, we just move EBP into ECX first because EBP is close to where I want it. I just have to make a minor adjustment by using an add instruction. So this way, ECX ends up to be the address of the buffer. And I only want to read 1 byte, so put that into EDX. So I have EAX, EBX, ECX, and EDX initialized at this point, but if I don't do the int instruction, nothing is going to happen. So you got to remember to do the int instruction here, just like that. Now, since the read operation is on the left-hand side of a logical AND, I have to check EAX first. Because if EAX is a 0, I need to get out of the loop right away. So here we have to do a compare. 0 with EAX, which is the return value of read. And if it is 0, we need to exit. So we have to go to while end. So while end is going to be here, and right before that is an unconditional branch back to while begin. Okay, so if the read operation returns a non-zero, which in this case can only mean that I have just read a character, then we can just go ahead and compare what I have just read. Is it a digit? So we'll check that. So once again, we have to do a compare. But this time you have to be careful because we have been using long all along, but this one has to be compare byte. Because buffer or buff is just a single character. If you use a compare long, depending on what the other 3 bytes are, it might work out just fine or it may not work. So we want to use compare byte to remove that uncertainty. So we want to compare the ASCII code of 9 versus buff itself. Buff is my local variable, so it's going to be relative to EBP. And we want to say if it is greater than, then we get out of the loop. So now is the question, is char signed or unsigned?
Unsigned. So he's above.
It is signed. The C interpretation of char is actually signed. Don't ask me why, but it is. So because it is signed, so instead of using JA, which is greater than, we have to use JG because that's the signed interpretation of greater than. So we have to say, okay, in this case, we get out of the loop. Once again, go to while end. And then we have to compare it again, but this time using the ASCII code of 0. And we say if buffer is less than the ASCII of 0, also go all the way to the end, exit the loop. So that takes care of the condition of the loop itself. Now what is left is to do that equation inside the loop. So the equation inside the loop involves multiplication, and also it involves a subtraction. The multiplication in this case is not too bad. There is a way to do this without actually the mode instruction. In fact, let's do it without the mode instruction, okay? Because multiply by 10 is not too bad. We can do it without the mode instruction. All right, so let's do that part first. How do I compute 10 times result without using the mode instruction? We can add result to something 10 times.
Yeah.
But that would be pretty excessive. We can do it. We can do much better than that.
Set up a loop.
What is 10 as a sum of powers of 2? 10 is, how do you express 10 as a sum of powers of 2? Okay, look for the largest power of 2 that is less than or equal to 10. That's
2 to the third.
Yep, exactly. 2 to the third plus
2 to the first.
plus 2 to the first, okay? Because it's 8 plus 2. So how do we make use of that to calculate result times 10?
Power function.
No. Multiply by 2 is easy. Okay, let's check this out. So before we do anything else, let's stick it into a register first. So we stick result EBP into a register. Let's call it EAX. Okay. So one way to do this is to say, okay, we'll just have to add it 10 times. But we don't want to do that, right? Go ahead.
You need to shift the bytes.
But we haven't talked about a shift instruction, but we have something that is similar to a shift. What about this? What is the effect of adding EAX to EAX?
Double.
Is doubling, and how does doubling relate to shifting? This is left shift by 1 bit. It's just not called shifting. Okay? Okay, so once we have done this, we want to store it because this is one tap point. Okay, so we want to copy this to another register, so we'll just copy it to EDX. Because this is 2 times the result already. And then what we do is we do it one more time. This is 4x. This is 8x. So by the time we get to the third NL EAX to EAX, this is 8 times, so we add this EAX to EDX, which already had the 2x. So when you add the 2x and the 8x, guess what? You have the 10x. So we have 10 times result currently in EDX. Is that okay? Or not? Okay. So now we just did the multiplication without using the multiplication instruction. Why would anyone do something like this? It looks kind of insane.
A RISC architecture?
Well, a RISC architecture typically has a multiply instruction now, because we have fairly advanced, processors. What if you have an 8-bit processor that does not have a multiply instruction? Then you have to call a subroutine to actually do multiplication, going through loops, shifting, and stuff like that. This is a whole lot faster. Okay? So this is actually applicable sometimes depending on what kind of architecture you're working with. But I do want to show you this code because it's based on instructions that we already know. It's just a trick to make use of those instructions. Okay. So what is remaining is buff minus 0, which is this part of the C code. Looks very simple, but it's not. Because it has to do with the extension of a byte into a 32-bit thing. So to do this part, there are a few ways to do it. The first one is to extend buff first into a 32-bit thing, and then we do the subtraction. Or you can do the subtraction and then expand. So it's your pick to choose how you want to do it. Either way, we have to put 0 into a register first, and I choose to do it the first way, which is moving buff into the least significant byte of EAX. So at this point, EAX is guaranteed to have 24 zeros as the most significant bits, and only the least significant 8 bits is the register. In other words, we have a clean 32-bit number that we can do a subtraction. So now we can do a subtraction. So we're subtracting the ASCII code of 0 from EAX. But we can do it safely now because we already know that EAX is a clean 32-bit value. So after the subtraction, we have the value that we want to add to EDX. So we add EAX to EDX, and then store EDX back into result. And that should be the end of the loop, the content of the loop. And at the very end here, after the exit label, the only thing we have to do is to move result EBP into EAX because we still want to return it through EAX. Are there any questions about this code? I think this code has about 95% of stuff that we already know, and only about 5% of stuff that we are trying to understand in today's class, which is this bunch of instructions. Are we doing okay? Are there anything I should explain here a little more, or are we good?
What are we doing when we move EBP into ECX?
That's which line?
15.
Line 15? ECX is supposed to be the address of buff. Okay, so let's look at it from the kind of graphical perspective.
Okay, I get it.
You get it? Okay.
Yeah, good.
Because it's kind of the same trick that we do with the current homework assignment, because you need to use the address of a parameter to use map copy. It's the same thing.
Okay.
All right, so I think this code is good to go. The only thing left to do is to keep the prototype, but comment out the C definition of the subroutine. And remember to add a semicolon over here. So we have GCC-O read 10, read 10.c, R10.uppercase S, and we have to supply a -G so that we can run it in GDB. And it doesn't work because I'm in a 64-bit architecture. I keep forgetting that. Okay, so we have to start up a new virtual machine. Hey, I have it already in the right folder. Good thing is the emulator works a lot faster when I'm using Linux as the host operating system.
If you putty into the emulator, it's not nearly as slow. Why is that?
No, if you putty, it's still the same speed. It's just that, you know, the startup process is a lot longer. So by the time you can putty, it's already done with the startup process.
But I mean, when I'm running the machine, it takes like a second for every keystroke to go through, unless I use putty.
Mm-hmm.
That
User
can
interface
be
speed.
because the console, okay, I can see what you mean. So you're basically saying if you do it in the console, which is you know, this thing here, is using the graphic stuff from the emulator perspective, but when you're doing it in putty, it's more native to Windows. So that's why it's more efficient. But in Linux, it wouldn't make any difference. All right, so what we need to do is to copy everything over, or just type everything over, which I'm not gonna do. So we'll do the same old trick, CZVF, you know, dash, test, pipe to, oh, do you think this pipe has anything to do with that pipe call that we saw earlier as a service they can ask the operating system?
Yes.
Absolutely. Do you think this command line here involves fork? And the answer is yes. So every time you run anything from bash, it's going through fork. So the parent process would just say, okay, I'm just going to wait for the child process to be done. And then the child process is going to try to figure out, okay, what are you trying to run? In this case, tar, right? So it will run tar by replacing the process with another image. So it is the same process, but it's no longer bash. It will replace itself with a tar image. That's how you run the program, or you start a new, quote unquote, start a new program in Linux. So what we want to do here is to do a tar xzbf a dash. Okay, I think that should do it. Nope. Oh, it's asking for the password. Is it user?
Yeah.
Yep, there we go. So now if I SSH into the virtual machine, we should see those files. So SSH-P 2200 user at localhost. Yep, everything is here. So GCC-G-O read 10, read 10.c, R10.uppercase S, GDB read 10. Okay, do we feel lucky? Do we want to just put a single breakpoint on line 24?
Yeah.
Yes.
And the program, 567, that's the enter key. No crashing, that's good. Print X, it is 567, so it does work. Every time I see a program working the first time, it's a mixed feeling. The first feeling is, yeah, that worked. And the second feeling is, oh, well, only worthless programs work the first time. And I'm slowly expanding the set of worthless programs.
Should it make me feel better that I've never had a program work the first time?
Then all your programs are worthy. They're not worthless. None of your programs is worthless. Which is, in many ways, is true because you guys are learning from the homework assignments. So every time your program doesn't work, what do?
Learn something.
You try to figure it out. But how do you figure it out? How do you figure out, why your program is not working, or how do you fix a program that is not working? Do you just do it again and again and again?
It's some combination of witchcraft and tears.
Okay, I can accept that. There's some kind of black art involved.
Precision guesswork.
Precision guesswork. Well, there's always a guesswork involved, okay? Because when your program stops working, there's an immediate symptom, right? There's a line where it seg faults, right? Typically in a program like the previous program, there's a place where you can see, okay, it's seg faults, it's not working anymore. But from that point, how do you proceed? There can be many reasons why it's seg faulting.
I see what's in the registers.
Yep, but you have ways to choose, right? Which register do you examine first? Well, you have two choices. You can do IRESP, check the stack pointer. You can do IREBP to check the frame pointer, right? Once you check these two, how do you proceed?
Like checking the other registers I'm using before I.
Okay. Or you can look at the memory. You can look at a memory dump and say, okay, tell me the 16 things that the stack pointer is pointing to, assuming your stack pointer is still healthy. Because this will tell you something about the stack or the call frame at the time, or you can change this to EBP, which is only a certain portion of the call frame because it doesn't show you the local variables, only the parameters, the return value, address, and also the return address. But at any point you have ways to choose. What do I want to look at next? That's your choice. That's what you call the intelligence guess. The more you write the programs, the more experience you get, and you go like, okay, it's most likely something messed up over here. So you choose how you look at your program, how you examine the program. So every single time your program doesn't work, it's actually a learning opportunity. As long as somebody doesn't try to do the same thing over and over again and expect it to change. Did anyone write the previous homework assignment the first time and it works?
Some of it.
Okay, some of it, but not the entire thing, right? But every single time you make a mistake or every single time the program crashes, what is the result of that? Other than frustration, but after the frustration and...
The main one was giving up and then getting an extension on the deadline. So.
Okay, but eventually, what did you end up doing?
Like you're
Fixing it.
You're fixing it, but how do you fix it?
well, you gotta like figure out where the source of the problem is.
Gotta
Right,
figure out how to use
okay.
GDB properly.
Using GDB first, figure out the source of the problem, and then once you figure out the source of the problem, that's the majority of the work, right? Because once you know what the problem is, figuring out the fix is usually pretty easy. So I can tell you that you're already doing better than most students at UC Davis when I was a TA over there. When I was a TA over at UC Davis, and I was a TA for CISP 360, or what is equivalent to CISP 360 here. And I went to the lab at about 11 p.m. Because the lab over there is 24/7. It's open all the time, except the air ventilation stopped at 10 o'clock. So now you have a whole bunch of people with old, hot, computers, and it's not a good place to be in. And when people quote unquote debug their programs, guess what they do? Now this is only based on one observation, okay? But at least I can talk about this one specific observation. They make random changes to the program and hope that one of the random changes will fix the program. So what kind of random changes are we talking about? They changed less than to less than or equal to, compare to 0 to compare to 1, changing the ordering of the statements, like swapping the orders and stuff like that. And that's how they quote unquote debug their programs. Yeah.
Like pretty much this is the first class that's ever had me use a debugger like in programming, so.
That's because you have much better professors in all the other classes because they never really realized that they need to use a debugger. I'm not that good of a programmer. Okay, when I write programs, I always have bugs, so I have to learn how to use a debugger to debug my programs. Is that making any sense?
No.
Yes.
I'm picking up what you put down.
Because if someone has never written a program where there are bugs and they have to debug the program, they will never find a use of GDB. I mean, who would read this for leisure. Well, actually, yes, I would. But in general, this is a tool. This is a really useful tool for debugging, but it is still just a tool. You have to be the one steering, to make use of the tool. Okay, so this program works. Are there any questions about this program or how to interact with the operating system? So if I have to sum up, if you have to sum up how to interact with the operating system, what would you use as one single instruction? Int $0x80. Okay, that's the one single entry point to talk to the entire operating system. So what are the chances that someone can find an exploit? Okay, first of all, how much is exposed? Is it a big exposure or a small exposure? It's a very small exposure.
Are you sure there's only one way? That's the only way?
Yep. Out of the entire Linux kernel, this is the only interface for an application program to interact with the operating system.
So you can't fool it like you fooled, when you fooled those other programs into believing that that was the entry point. When you were hacking a program.
You cannot hack int very easily because when you use int, it doesn't even use your own stack.
Oh.
So the moment you run the int instruction, the system will switch over to the kernel stack, and as a result, you don't even know what is going on past that int point. You cannot look back into the stack and say, I can figure out, you're doing this, you're doing that, and whatnot. You don't get a clue of what is going on after you execute the int instruction. Yep.
So basically, like, if you get a piece of code from somewhere that just has an int in it, then that can make call that you don't that has an int instruction that you don't know about, that can actually call into your operating system and do things, right?
Okay, say that one more time.
Well, it's pretty much like an int command written into a program that's it's hard for me to explain, but an application that's so assembly code makes use of the int thing int instruction can in fact if you
like it interrupts in the program.
Yeah, exactly,
like they hide an interrupt command somewhere in the program.
Hide an interrupt command in the program. Like not using int, but has the effect of int.
Well, not really not using it, but there's an interrupt program that you just didn't know about for some reason or other.
Oh, I see. So you're trying to discover undocumented features of the operating system, something like that?
Well, or a program or whatever else.
Well, in this case, it is easy for the operating system to defend itself because the operating system just go by this table, right? So if EAX does not have one of these values, and this may look like a long list to you, but nonetheless, EAX is a 32-bit register of which only 190 values are used. So the first thing the operating system is going to check is to say, is EAX within the right range? If it's not in the right range, it's just going to do something, well, let's find out what it's going to do. Because we're only supposed to have these system calls. So that means if EAX has a value outside of this range, the operating system should do something that is safe and possibly crash your program so that your program cannot continue execution. Does anyone want to find out what the program is going to do?
Why not?
I want to find out.
Coincidentally find an undocumented feature? That'd be interesting. Don't think it'll happen.
That's not going to happen.
There's a lot of
because
additional
Linux has been
features.
around for too long to have that type of problem still existing. Okay, as I modify this program as I'm hacking it, let me ask you another question. What about the GUI? what about this graphical user interface? You know, how do we draw stuff? You know, is it also going through int, you know, $0x80, or is it going through some other mechanisms? Like this is like 3,000.
Isn't there like a whole matrix in there?
A whole matrix?
Yeah.
Mean
Need
like,
somewhere deep inside.
Somewhere
like,
you-
or are you referring to the raster display?
Yeah.
Okay.
It's-
Well,
it's
but
not
how do you put a pixel somewhere? How do you draw text on the screen?
Well, you have a point in space, and then you just, navigate around it.
But does your application get to control the video card, or how does your application program deal with the graphical user interface? That's the question. What is the interface? Do you call something at the lowest level? Do you call something, or how do you interact with the Windows graphical user interface system?
I crashed. I don't know.
I guess like what he's asking, like when you move the mouse, how does the GUI know to like update that as?
Or in your application, if you want to draw a rectangle on the screen, you know, what do you do to draw a rectangle on the screen? Now, some of you already know OpenGL or some of the libraries, but that's just a library, okay? It's just one way to talk through that interface that is easier to use. But at the lowest level, it's done through a socket. It's done through a networking socket. In other words, all the commands to show something on screen, to figure out where's the mouse and stuff like that, it's all done through serial communication. It's all done through a certain network port, which also means Linux is actually easily set up to run the program remotely. You can run what we call a client program remotely and have the local computer as only for display purposes, as a dumb terminal. That's how it's set up. Okay, so we want to look at this program and see how it's going to crash. So we'll say /. I want to see how it crash outside of GDB, and it just doesn't do a single thing. Okay, it doesn't crash, it just doesn't do anything. Okay, so now we want to get into GDB and figure out what is EAX returning. Yep.
Is there a way to get an exit code when you run it in the terminal? Can you ask?
Shouldn't there be a flag?
Okay, what do you mean by the exit code?
Like,
The actual exit code, the 0?
Yeah.
Yes, but I cannot remember how to do it. But that's why we have Google. Okay, bash exit code. Okay, exit and exit status. There's a dollar something, dollar question mark, I think. Yep, there we go. So dollar question mark, echo dollar question mark, there we go. So in this case, it's returning 11111111 because that's what 127 is. So the program did not exit normally this time because I specified an exit code of 0. It was not using my own exit code. The program actually exit probably at the time when I do the first int $0x80. So the only way to confirm that is to use GDB. So we use GDB, go into read10, and we want to list the assembly code because it's then going to be the assembly code. And the place that we did that call for the interrupt is on line 18. So we'll put a breakpoint on line 18 here. Run the program. We're ready to make that call. So my guess is the single step here is going to exit the program and it's not going to say normal. Okay, single step. Oh, okay, that did not happen. So the question is, what is EAX? EAX has a negative value, which means it's the operating system is trying to tell me something, it's not working. The normal exit code is usually a 0. It's just a convention. So when it's non-zero, it is something else. So the question now is, why did I get an exit code of 127? Okay, so we'll just continue. And it still said it's exited normally. So that one did not come from here. Okay, in GDB is a different way to find out what is the exit code. Okay, let's find it here. done through what we call a variable. So exit code variable, that should do it. Convenience variables, okay. And then we look for exit. So underscore, $_ exit code is when the program being debugged terminates, normally GDB automatically sets this variable to the exit code. Okay. And we'll give it a try. Underscore exit code. Plain $_ exit code. And it is 0. So that means the other program would have done it too. Run the program first, and then echo $0, and that's a 0. So the program did normally exit. It's just that when I request Surface 3000, the operating system just returns and go like, don't know what you're talking about, go away. And did not do a single thing. But as I said, it's easy for the operating system to defend itself because there's only one point of entry. So when you only have one point of entry, there's only one point to start the defense, to say, okay, let's check all the registers. Let's check whether this is actually okay or not. All right. Any other questions? Yep.
How do you go up there and never come back?
Go up there and never come back. What do you mean?
The levels. How do you hop into a different level and
How do you
some
retain your priority?
Dirty work there. And there's a way, isn't there?
Well, you can run SU and change to root privilege, which starts a new shell. Okay, that's one way to do it. But in a program, I don't think there are ways to elevate your privilege level.
Levels?
Yeah, you might be able to do this. Let me see if I can find it. If you can change the user ID of the process, that will basically do the same thing. So let's see, UID, set UID. That might do it. Set UID. Because you're changing the user ID of the process. If you can change the user ID of the process to root, then the process is running as root, which means now you have access to the whole operating system.
Nice.
But that would not work unless the permission is already allowed. So let's see let's figure out how to use a set UID. Set user identity. It will set the effective user ID of the calling process. If the effective UID of the caller is root, the real UID and saved set UID are also set. Okay. And look at the return value. On success, 0 is returned on error, -1 is returned, and error none is set appropriately. And it only requires one single operand or one parameter, which is the user ID that you want to switch into. You guys want to see what happens when I say, hey, let me be root? Okay, let's try it. Okay. And you can see that when I teach the class, a lot of stuff I don't know exactly what is going to happen. But in this case, pretty sure it's going to return a -1. But I have to find the terminal where I am inside the emulator, which is this one, I think. Let me check. Yep, that has to be the one. Okay, so let's see. I'll just call it SU. We want to move, okay, what is the register value? 23, okay. So we put a 23 into register EAX because it's surface number 23. We move a 0 into EBX because the user ID of root is 0. Well, I better check that too. I'm not 100% sure.
So
Yep.
you can log yourself out with a little assembly program?
No, you cannot lock yourself out. I mean, it will simply come back and say, nope, not going to happen. Okay. So this should change the privilege level of this program to root, and then we'll go ahead and specify the usual stuff to exit the program. Okay, so this program will do two things. One is to SU to root, and then the second thing is just going to exit. Okay. AS G stabs. link. TDSU. Okay, the program exited normally, so it didn't crash out. But I want to check what is the return code, so I will put a breakpoint on line 7 to check EAX. So run the program, and now I can print or IR EAX. What do you guys think EAX should be? If it was successful, it's a 0. If it's not successful, it's a -1. So what do you think it should be?
-1.
Should be -1. Yep. And there it is.
Told you to go after yourself.
Yep.
If you had run it while you're logged under SU, would have been 0, right?
Say again?
If you had run it as an admin,
Correct. Or you can set UID to yourself. That would still be okay. That should still be okay. So let's check that too. All right. So the current user ID. Okay. Let me show you how to check that. So the current user ID is 1000. Okay. This is actually my current user ID. So we'll go ahead and change that to 1000. Which should be okay, because I should not have a problem of changing the user ID to what it is already.
was that the surface change?
Oh, that's right, okay. Change this one, there we go, thank you. And then we'll repeat the assembler, repeat the linker, and GDB. Yep, okay, that's correct. Put it breakpoint on line 7, run it, IREAX, and this time it's a 0 because there's no problem switching the user ID to what it is already. Okay, so let me stop the recorder first because I'm going to do something